All right, let's talk about one of the most important foundational building blocks in modern software, the message queue. Honestly, it is the secret sauce behind pretty much every scalable and fault-tolerant system you use. If you're building anything distributed, you absolutely need to know this stuff inside and out. So, let's get into it.
So, picture this. It's the biggest shopping day of the year. Your order service is just on fire, taking thousands of orders every single minute. But oh no, your payment service, the one that has to talk to some slow third-party gateway, it suddenly starts to crawl. So what happens next? Well, in a typical setup, your order service just waits, and pretty soon, the whole system starts to buckle and fail.
What just happened there? Well, that's a classic coupling catastrophe. See, when your services are all chained together with these direct synchronous calls, it's like a line of dominoes. One tips over, and the whole thing comes crashing down. And the math here, it really tells the story. Even if you have two services that are each 99.9% available, your total system availability actually drops to 99.8%. A tiny failure in one spot creates a much bigger problem for everyone.
So how do we stop that from happening? How do we break the chain? We need something like an architectural shock absorber. And that, my friends, brings us to the decoupling revolution, all powered by message queues.
At its heart, a message queue is actually incredibly simple. Just think of it as a buffer, an intermediary that sits right between your services. So instead of Service A calling Service B directly and waiting for an answer, Service A just drops a message into the queue and that's it. It moves on. Service B can then swing by and pick up that message whenever it's free. They never even have to know each other exist.
And this one simple change, it is a total game changer. It unlocks so many powerful benefits. Your order service can now scale up like crazy to handle that holiday traffic, while the payment service just chugs along at its own steady pace. The producer, our order service, gets this massive performance boost because it's not stuck waiting around. And what happens if the payment service goes down for a bit? No problem. The queue just holds onto those messages safe and sound until it comes back online. That right there is the magic of decoupling.
Okay, so how does this whole thing actually work under the hood? Let's pop it open and take a look at the anatomy of a message queue. There are really only three main parts you need to get.
First up, you've got the producer. This is pretty straightforward. It's the part of your application that needs something done. It bundles up the work into a little packet of data, that's the message, and just fires it off to the queue. So in our Black Friday story, the order service is our producer.
In the middle, you have the broker. This is the heart of the whole operation. It's the message queue system itself. You've probably heard of things like RabbitMQ or Apache Kafka. Its main job, its whole purpose in life, is to store those messages safely and reliably, usually by writing them to disk, until someone is ready to deal with them.
And finally, of course, we have the consumer. This is the worker bee. It's the component that connects to the broker, grabs a message from the queue, and then actually does the work. So in our scenario, the payment service is the consumer.
So let's put it all together and trace the life of one single message. The producer sends it, the broker stores it, a consumer grabs it, and then, now listen up because this is the most critical part for reliability, after the consumer successfully finishes the work, it sends a little signal back to the broker called an acknowledgement. Only when the broker gets that ACK does it actually delete the message for good. That tiny step is the key to making sure no work ever gets lost. All right. You've got the basics, but not all messaging is created equal. There are two main patterns or models you're going to see out there, and picking the right one is absolutely crucial for your design.
So you've got two main flavors. On one side, you have the point-to-point model, which we almost always call a work queue. The rule here is simple. One message gets processed by exactly one consumer. It's perfect for dividing up a big pile of work. On the other side, you've got publish-subscribe, or fan-out. This is totally different. A message is published to a topic, and every single service that's subscribed to that topic gets its own copy. This is all about broadcasting events.
Let's dig into that point-to-point model a little more. The best analogy is a shared to-do list for a team. A new task gets added to the list, and any team member who's free can just grab it and start working. In tech terms, this means you can spin up multiple instances of your consumer service all reading from that same queue. We call that a consumer group, and it is the fundamental way you scale your processing power horizontally. Just add more workers.
Now, on the flip side, we have publish-subscribe. The newsletter analogy here is perfect. Let's say an order-placed event happens. The producer just publishes that one event to a topic, then the shipping service, the analytics service, the notification service, they might all be subscribed. And each one gets a copy of that event and can do its own thing with it, completely independently. The beauty here is that the producer has no clue who's listening.
It's just shouting into the void. And that's the real cornerstone of a powerful event-driven architecture.
Okay, theory is great. But what happens when you're running this for real, with real users and real money on the line? Well, you've got to start thinking about some more advanced, real-world concepts to make sure your system is truly bulletproof.
The first and maybe most important concept here is delivery semantics. Basically, this is the promise, the contract that your message queue makes to you about how a message is going to be delivered. Is it guaranteed to arrive? Could it arrive more than once? It's a really important question.
And this brings us to a huge trade-off. Most systems you'll encounter give you at least once delivery. This is great. It guarantees your message will get there. But it also means it might get there more than once. Imagine a consumer processes a message, but crashes right before it can send that ACK. The broker will think it failed and will just redeliver it. Now, the holy grail is exactly once delivery, but that often comes with a big performance penalty. So you really have to think about whether you need it.
And this leads us to what is probably the single most important rule when working with message queues, especially if you get asked in an interview. If you're using at least once delivery, your consumers absolutely must be idempotent. Idempotent just means doing the same thing multiple times has the same effect as doing it once. Think about it. A payment service has to be smart enough to ask, hey, have I already processed transaction 123 before it tries to charge the card again? If it doesn't, you're going to be double charging your customers, and nobody wants that. Okay, here's another real-world problem for you. What if your producers are just way faster than your consumers all the time? Well, that queue is just going to grow and grow until it runs out of memory and crashes the whole broker. That's where something called back pressure comes in. It's a safety valve. The system can actually tell the producer, hey, slow down, or even stop it completely for a bit, which gives the consumers a chance to catch up and keeps the whole system stable.
So what do you do with a message that just can't be processed? You know, maybe the data is corrupted or something. No matter how many times your consumer tries, it fails. We call this a poison pill message. You can't let it just sit there and block everything else forever. The solution is brilliant, a dead letter queue, or DLQ. After a few failed attempts, the broker just moves the poison message over to this separate queue. That lets the main queue keep flowing, and later on, an engineer can go look at the DLQ and figure out what went wrong.
Phew, okay, that was a lot of ground to cover. So let's try to distill all of this down into a simple, clear checklist. When should you reach for a message queue in your architecture? And maybe, when should you hesitate?
So when is a message queue your best friend? Well, anytime you need to do work asynchronously. Anytime you want to decouple services so your teams can build and scale them on their own. And they're fantastic for smoothing out spiky workloads. Basically, they are the absolute backbone of reliable, modern, event-driven systems.
But, and this is a big but, message queues are not a silver bullet. You're adding another piece of infrastructure you have to manage and monitor. You have to design your consumers to handle duplicates. Debugging a request that hops between 5 different async services can get really tricky. And finally, you're buying into eventual consistency, which means things will be correct eventually. For things that need to be updated instantly and transactionally, a queue might not be the right move.
And that's the final thought I want to leave you with. Dropping a message queue into your system is a huge step forward. It decouples your services, which is great, but is your system now truly resilient? Well, decoupling is just the start. Real resilience, the kind that lets you sleep at night, comes from deeply understanding these trade-offs. It comes from building idempotent consumers, handling back pressure, and using tools like dead letter queues to manage the inevitable messiness of the real world.